GameSide.com. GameSide.com.
Heidi ho, campers, and welcome to the lesson on hash tables. The fastest data structure. Calculate, not search. Big O order of one notation. A normal array stores data by position. The element in slot 4 is between slot 3 and slot 5. A tree stores data by relationship. The element containing 40 is between elements 30 and element 50. A hash table calculates the location of the data to store and retrieve it. Number 1, a hash table is based on the array data structure. Number 2, data is stored in a hash table array using a key. Number 3, to place data into a hash table, use the key to calculate an index in the array and store the data there. Number 4, to retrieve that data, you need the same key, do the same calculation to find that same array index. Let's see where we might use a hash table. Let's use a game scenario, a massive online game where we need to track thousands or millions of users. We want to store a record, a set of information for each user that's logged on to the game. We're going to keep a record. A record's going to be composed of a screen name, which is a possible key for our hash table. What do you call yourself when you log on to the game? We're going to have a player ID. This is going to be a simple number. This could also be a key. This will be our internal tracking number for each player that has an account on the game. We're going to keep track of the level of the player is on, the virtual cash they have on hand, the money they can spend during the game, the actual dollars they've spent. That is the money they've paid to the game for access to it. We're going to keep track of a whole bunch of information, and the entire set of it is going to be called the player record. And two important pieces of information would be the screen name or the player ID, which are possible keys for our hash table. In order to store and retrieve data from a hash table, you're required to have a key, and those are the two different keys we're going to look at. We're going to store users in the hash table. When the user logs on, we'll put them in the hash table and we'll retrieve their data from the hash table in order to modify it during the gameplay. If we're constantly hitting our database during the game, it's going to slow it down. So we're going to hit the database at the beginning when they log on, load all their information, and then internally keep track of that information in a hash table. When they log off or in periodic updates, we'll write the data back base. Let's look first at storing new data in a hash table. Slot number equals hash of record.key. Hash is a function that takes a key as an input and returns the index or slot where we want to store that key record. What this is telling us is in position 9 of the hash table is where we want to store this record. Hash array of slot number equals record. We'll place the key and the entire record into the table at index or slot 9. That's it. It's really simple. A function will tell us where the data should go, and then we'll put the data in that position. Later in the code, we need to retrieve the player's record. Now it's time to get that same data out of the hash table. Slot number equals hash of record.key. We're going to call the same hash function, pass it the same key, and it will return the same result, position 9. The arrow pointing to the right shows we need to go to position 9 and retrieve the key. At position 9, we'll retrieve the key, the left arrow, and store it back into our record. Future slides will just show the key being stored and retrieved, but keep in mind the entire record, which includes the key, is typically placed into the hash table. I always use the simplest examples I can, so I'm going to show you a simple number or string stored into the hash table. But keep in mind, in a real world application, we're going to store a whole bunch more information in there. Let's look at an easy hash function. Remember, hash tables are the fastest data structures. They calculate, not search for data. They are big O order of ones fast. The critical factor in creating a hash table is a good hash function, whose job is to take a key as input and return an array index to store the key. So we're going to take hash1 as our function and pass it an input key. It's going to send as output an index where we want to store the data. So if it says return 4, store the data at position 4 in the hash table array. What happens inside hash1 to return the index/slot to store the input key? Some general rules for a hash function. Number 1, a hash function must return the same output given the same input. It must be consistent every time. Number 2, a hash function must be fast. If hash tables are to be order of 1, a hash function must be order of 1. Number 3, a hash function needs to distribute the data evenly. We need to spread out the data that is stored in the array. Let's go back to our game scenario. It's a massive online game. We need to track thousands, if not millions, of users to this game. Let's use a player ID number as the key. These examples use hard-coded values because it's easier to see where they'll go in the table. However, in a real program, you're going to use variables to store the information. Now, numbers are very easy to hash. We'll use what's called the modulus or percent operator, sometimes called the remainder operator. This will be the player ID number that we talked about in a previous slide. Each user that signs up for a game is assigned a unique integer that identifies them so we can track them during the game. And of course, we can track the money they've spent or the money they've paid into the game. Understand how we use player ID, we need to look closely at integer division. Integer division has two answers. When I do 7 divided by 2, the answer is obviously 3, but it also produces a remainder of 1. With integer division, there is no decimal point. We don't calculate a floating point answer. We say 7 divided by 2 equals 3 with a remainder of 1. Well, the modulus just directly calculates that remainder. 7 modulus 2 equals 1. If the remainder, when I divide 7 by 2, is 1, then 7 modulus 2 equals 1. Let's look at it again. 15 divided by 6 equals 2, with a remainder of 3. 15 modulus 6 directly equals 3. All we're doing is directly calculating the remainder using what's called the modulus operator. 7 divided by 8 equals 0. 8 does not fit into 7 at all. But when using integer arithmetic, it would have a remainder of 7. So then 7 modulus 8 equals 7. Simple. Calculate the remainder after doing division. That's all the modulus operator does. Now the modulus answer must always be less than the second operand. Think about it. If I were to take a player ID number and do a modulus of 13, how could the answer be 13? There's no such thing as a remainder of 13 after you divide by 13. It couldn't possibly happen. What if I took a player ID and did a modulus on 13 and got a remainder of 14? Once again, this is impossible. The remainder has to be less than the second operand. If you do a modulus on 13, it cannot be 13 or larger. The remainder has to be smaller than the second operand. What could the remainder be? If I did a player ID modulus 13, the smallest answer I could get is 0. If player ID is a factor of 13, when I divide by 13, I'll get a remainder of 0. That is the smallest answer I can get as a remainder when I divide by 13. Well, what about on the other side? If I do a player ID modulus 13, I could get a remainder of 12. That is true. But 12 is the largest number I could possibly get. When you think about it, when you do a player ID modulus 13, the answer has to be between 0 and 12. Those are the only possible answers. The smallest is 0, the largest is 12, and any integer number in between is a possible answer when you do a modulus of 13. Well, that answer between 0 and 12 makes it a perfect index or slot for an array of 13 items. If you look at the array over here at the right, indexes start at 0 and they will go to 12. An array of 13 items will have an index between 0 and 12. Well, that's what the modulus returns. When you do a player ID modulus 13, you'll get a number between 0 and 12. And that's why we use the modulus operator to calculate the position of the item in the array. It produces an array index where we can store our data. Now let's look at an example here. We're going to say slot equals hash 1 of 123. Calling hash 1 and asking it for the index or slot to store 123. Using the hard-coded 123, we can see the math. But keep in mind, this is a player ID we wish to track in our online game. We don't typically pass hard-coded values to hash functions. We pass variables and their contents. If we trace what happens inside the code, we're going to take the key that we passed, 123, and do a modulus on 13. This will calculate the position in the table or array where we want to store key 123. If you do the math and divide 13 into 123, it goes into it 9 times with a remainder of 6. The slot number we're going to return is 6. Well, that's exactly where we want to store the key 123. Insert the player ID or key in the slot hash 1 returns. Keep in mind, we may be placing the entire player record into the table, but we're only showing you the key 123. Let's do a slot equals hash 1 and pass it the parameter or argument 456. So we're calling method hash 1 and asking it for the index or slot to store key 456. Using the hard-coded 456 so we can see the math, but keep in mind this is a player ID we wish to track in our online game. We are saying, where should I store player ID 456 in the hash table? Send that as a parameter to hash 1. Doing the math, we want to store it in the remainder of 13 divided by 456. So 13 goes into 45 3 times. 45 minus 39 is 6. Drop the 6 down. 13 goes into 66 5 times, or 65. Subtract the 65 and we get a remainder of 1. We're doing simple arithmetic here. When you divide 13 into 456, our remainder is 1, so that's what we want to return. The 1 is returned and assigned to the variable slot. At that point, hash array of slot equal 456 will insert the player ID or key in the array slot hash 1 returns. Keep in mind, we may be placing the entire record for player ID 456 into the table, but we're only showing the key. Again, hard-coded values are great for seeing the math, but rarely used in actual computer programs. It's better to pass a variable to hash 1, and then let's also change the 13 that we hard-coded before to the length of the array. Hash functions always do a modulus on the array size, so they return a value from 0 to length minus 1 of the array. So let's improve this code just slightly by using variables rather than hard-coded values. But the result is the same. Let's say slot equals hash 1 of the player ID that we wish to store in the hash table. We'll pass player ID or 789 as the parameter hash 1. Using a parameter with the value 489, which most likely came from a database when the player logged on to our online game. Once again, we got to do a little math. No one ever promised you there'd be no math involved in computer science, and we have to understand the math to understand the hash table and the hash function. So let's do this calculation. Key modulus array.length. Well, the key we passed is 789. The length of the array is 13. We need to do a little division and calculate the remainder. 13 goes into 78 6 times, and it perfectly goes into 78, so it has a 0 here when I subtract out the 78. We drop the 9 down. 13 doesn't fit into 9, so we'll put a 0 here, and we'll calculate the remainder of 9. When you divide the key 789 by 13, the remainder of 9 is calculated and should be returned to the calling routine and assigned to the variable slot. 789 needs to be stored in slot 9 of the array. Hash array of slot equals player ID. Boom, there's our 789 going into the hash table. We inserted the player ID or key into the array slot hash1 returns. Keep in mind, once again, we may be placing the entire player record in the table, but only showing you the key 789. When it comes to the easy hash function, look at our original 3 goals. Number 1, we wanted to return the same output given the same input. Every time I call slot equals hash1 of 1, 2, 3, it's a 6 every single time. Number 2, hash functions must be fast. Key modulus array.length is a fast function. It jumps straight to key 123 in slot 6 when it comes time to retrieving this data. That is a fast calculation. Number 3 goal for hash functions. Hash functions must distribute data evenly. Look at how this data is spread out. There's plenty of open space between it. One key to doing that is to use a prime number as the second operand to the modulus function. Data here is spread out between slots 1, 6, and 9. That's a good hash function. If all this data was bunched up, it would be bad. When the data is spread out, our hash function is good. Using a prime number as the second operand is very important. The array size of 13 was not an accident. Key modulus 13 will distribute the data more evenly than if I did a modulus on something like 10. Instead of using an array size of 100 and doing a number modulus 100 during our hash function, use the prime number 101 and do a number modulus 101. Modulus of the prime 101 produces better results than modulus of 100. Instead of using an array size 1000 and doing a number modulus 1000, use the prime number 1009 and do a number modulus 1009. Prime numbers distribute the data more evenly. Round numbers like 100 produce a lot of duplicate results, and we want to avoid that. We want our data to spread out and get its own position in the table. Always use a prime number when using the modulus operator in a hash function. String hash functions. What if we want to store our data using a string as the key in the hash function? Critical factor in creating a hash table is a good hash function whose job is to take a string key as input and return an array index to store the key. We'll build a new hash function, hash2. We'll pass it a string as a key. Once again, it'll output an output index, let's say position 4, and that's where we want to store string key. Now, what happens inside hash2 to return the index or slot number to store a string key? Number 1, we need to convert the string key to a large number. We have to come up with a formula to convert letters to a number. Number 2, we then use the modulus operator, so we can say the slot equals a large number that we just converted, modulus the array size, and come up with a position, and then number 3 will return that slot number to the user. Once again, we'll go back to our game scenario. We're a massive online game. We need to track thousands, if not millions of users who are playing our game. This time we want to use the player screen name as the key for storing the record in the hash table. When a person signs up for our game, they give their unique screen name. When they log on using their screen name. We're going to use that as our key. First step to understanding how to convert a string to a number is to understand numbers. If you look at the number 123, it can be broken down into equaling 100 plus 20 plus 3. In the third grade, your teacher taught you the 2 was in the tens place and the 3 was in the ones place of the number 123. Another way to look at 123 is it's equal to 1 times 100 plus 2 times 10 plus 3 times 1. Remember what your third grade teacher told you. 3 is in the ones place, 2 is in the tens place, and 1 is in the hundreds place. Breaking this down a little bit more, you could say 123 equals 1 times 10 squared plus 2 times 10 to the first plus 3 times 10 to the 0. Do you ever wonder where your third grade teacher learned about the ones place, the tens place, and the hundreds place? It's all based on powers of 10. 10 to the 0 power is 1, therefore 3 is in the ones place. 10 to the first is 10, so 2 is in the tens place. And 10 squared is 100, so the 1 is in the hundreds place. Well, if it works for numbers, and numbers, decimal numbers, have 10 unique digits, so it's based on powers of 10, we could do the same thing for letters. Let's use A equal to 1, B equal to 2, C equal to 3, and Z equal to 26, and convert a string to a number. We started A at 1. We could have started at 0, but we'll start it at 1. That means Z is going to be at 26. If we want to convert ABC to a number, we'll use the same breakdown we used up here. We'll take ABC and set it equal to A times 26 squared. There are 26 letters in the alphabet, so let's do powers of 26. Remember, there are 10 decimal digits, so we break it down at powers of 10. There are 26 alpha letters, so we'll break it down into powers of 26. A times 26 squared plus B times 26 to the first plus C times 26 to the 0 power. All we're doing is breaking the letters ABC up into their various powers of 26. Well, if you convert A to 1, remember A equals to 1, B equals to 2, C equals to 3. A is a 1 times 26 squared plus 2, which is B, times 26 to the first plus C, or 3 times 26 to the 0. All we're doing is breaking down letters exactly like we do it to numbers. Substituting in the powers of 26, ABC equals 1 times 676 plus 2 times 26 plus 3 times 1. Those are simple powers of 26. Completing the math, ABC equals 676. All I'm doing is this column right here. A converts to 676. B in this column converts to 52. 2 times 26 is 52. Plus 3 times 1. You add all of those together and you get 731. What this is telling us is that's the large number. We converted ABC to a number, 731. Now it's time to do a 731 modulus 13 and get the remainder. Well, if you do the math, look at it here. 13 divided into 731 goes into it 56 times. If it goes into it 56 times, according to my division here, the remainder is 3, and that's where we want to store ABC. Do you see it? All I did was convert ABC to a number using a formula. I then took that number and did a modulus on my array size, and it returned a remainder of 3, so that's where I want to store ABC. What you need to understand here is that C, which is really 3, is in the ones place. 26 to the 0 is 1, so I do 3 times 1. B, which we converted to 2, is in the 26th place because 26 to the first is 26, so we're going to do 2 times 26. And finally, A, using our formula, is 1, and it's in the 676th place because 26 squared is 676. Using this math, I converted ABC to a number, then used the modulus operator to decide where I want to store ABC in the hash table. Let's do some examples. Once again, I'm going to use hard-coded values like ace and bat. But again, hard-coded values aren't the best option. These would be values from variables. When the player logs on, we'd pull their screen name out of the database, and that's what we're passing to hash 2, the screen name of the player that we want to store in the hash table. We'll be calling method hash 2 to calculate the index or slot to store the key ace. Characters are stored using ASCII code. The ASCII code for the letter A is 97. The ASCII code for the letter B is 98. The ASCII code for the letter C is 99, and so on. So if I do an A minus 96, I'm really converting A to 1. When I do a B, which is 98, minus 96, I'm converting B to a 2. And finally, when I do a C minus 96, I'm doing a calculation of 3. All I'm doing here is calculating the value of each letter by subtracting it from the base value, the code for the letter A. Once again, I'm using a lot more hard-coded values than I like to, but hard-coded values are much nicer for seeing how this function works. So I'm going to use some hard-coded values in here to show you how it works. Here is hash 2, which calculates or converts a string to an array index. We're going to start with int value equals key.char at position 2 minus 96. I want to pick up the last letter of the key, that letter E. So I'm pulling the letter E out of my key right here. I'll subtract it from the ASCII value, 96, and I will get E's value. E is in the ones place. This is E times 26 to the 0 power. So when I calculate E as being in the 5th position of the alphabet, I'll do 5 times 1 and calculate a 5 for the letter E in the key. Moving on to the next letter, I want to get the character at position 1 of the array. I want to pull out that C. Well, C has the ASCII value of 99. 99 minus 96 converts C to the number 3. I then multiply it by the appropriate value of power 26. 26 to the first power is 26. So I'm going to do 3 times 26 and get a 98 here. Finally, I'm going to do the letter A. A has the ASCII value of 97. That's key at character 0 is the A. I do the A minus 96 and I calculate A as the value 1. I multiply it by 26 squared, or 676, and of course I get the value 676. Well, if I add up what E, C, and A convert to, it comes out to 759. So we converted ACE to 759, and now we have to do a modulus on 13. When we do 13 divided by 759, if you do the division, it comes out to be 58 with a remainder of 5. 5 is the value we want to return. Do you see what I'm doing? I converted ACE to a number. I then did that number modulus 13, and it says store your data at position 5 in the array. With the 5 in the slot number, when I do hash array of slot equals ACE, it will say at position 5, store the key ACE. We inserted the screen name or key ACE into the array slot 5 that hash 2 returns. Keep in mind, we may be placing the entire player record into the table, but I'm only showing you the key ACE. Try it again. Maybe it'll come out clear the second time. We're going to say slot equals hash 2 and pass it the argument bat. We're calling the method hash 2 to calculate the index or slot to store the key bat. This is oversimplified code so you can see the math to convert a string to a number. A loop through each letter of the key would be a better solution. It would handle longer keys. But right now I'm using very much hard-coded values as parameters and in the function so you can see how this works. Inside hash 2, remember we've passed it the key bat. We need to go through the letters in the key bat, convert them to numbers, and multiply them by their powers of 26. So when I do key.char at 2, I'm getting the position, the character at position 2. I'm extracting the T from the key. T is ASCII code 116 minus 96 is 20. Multiply that by the power of 26 to the 0, and I get the value 20. Turns out T is the 20th letter in the alphabet, so I calculate the 20 for the letter T. There's the letter A. We all know what the letter A is. The letter A is the value 1. A has an ASCII value of 97. So when I subtract 96, I get a 1. Multiply it by 26 to the first power, and I get 26. Let's grab the first letter of the key, the B. B is ASCII value 98. Subtract it from 96, and I've converted B to 2. Multiply it by 26 squared. 2 times 676 is 1352. Add all three of those numbers up, and I get 1398. The key bat converts to the large value 1398. Well, how do I map 1398 to a position in the hash table? I do a modulus of 13 and find the remainder. So after converting bat to 1398, I find the remainder by dividing 13 into 1398. Here you can really see the math. 13 goes into 13 one time with a remainder of 0. So I drop down the 9 and put a 0 above the 9 because 13 doesn't fit into 9. I drop down the 8 and create a 98, and it turns out 13 goes into 98 7 times. 98 minus 91 is a remainder of 7, and I say I need to store bat in position 7 of this hash table. So I will return the value 7 and assign it to the slot variable. When I do my hash array of slot equals bat, slot contains a 7, store the key bat in position 7 of the hash table. Insert the screen name or key bat into the array slot 7 that hash 2 returns. Keep in mind, we may be placing the entire player record into the table, but only showing bat going into the table. One more time, hard-coded values are great for seeing the math, but rarely used in actual programs. Better to pass a variable to hash 2 and change the 13 above to the length of the array. Also, we could calculate this value using a loop, and we'll see that shortly. But for now, I want to use this sort of hard-coded simple version of hash 2 so you understand how letters get converted to numbers, and then that number gets converted to an array slot. Assign name equal to con. So this time, when we do slot equals hash 2, we'll pass it a variable rather than a hard-coded value. Slot equals hash 2 of name. Much better. We're passing a variable instead of a hard-coded value. Calling the method hash 2 to calculate the index or slot to store con. This is oversimplified code, so you can see the math to convert its string to a number. Far better to use a loop through each letter in the key. Also, we need to avoid integer overflow, and we'll see how we do that too. Let's trace this code line by line. First, we're going to extract the character at the end of the key, the N. So we take our N, which has an ASCII value of 110, subtract it from the constant 96, which is the value for A, and it says N is the 14th letter of the alphabet. When we multiply that by 26 to the 0 power, we get 14. Extract the letter O from the key. O has an ASCII value of 111 minus 96. We multiply it by 26 to the first power, and we get the value 390. That's what this middle line of code is calculating. Then we extract the C from the key. C has an ASCII value of 99, minus 96 is 3. Multiply that by 26 squared, and we get 2028. Add all those together. Remember, plus equal says sum them all together, and you get 2432. We just converted con to 2432, and we're going to return the 2432 modulus 13. Well, here's the math. 13 divided into 2432 is 187. Again, I'm subtracting out the result, dropping down the 3 into 113. It goes into 8 times, subtracting out the 104, remainder of 9. Take the remainder of 9, drop down the 2. 7 times it goes into 92, and we calculate finally a remainder of 1. 13 divided by 2432 produces a remainder of 1, and that's what we're going to assign to the variable slot. The key con belongs into slot 1 of the array. Hash array of slot equals name, while slot contains a 1, so con needs to be stored in slot 1. We insert the screen name or key con into array slot 1 that hash function 2 returns. Keep in mind, we may be placing the entire player record in the table, but we're only showing the key con in the hash table. Now, I'm not saying that previous function was bad, because you need to see it that way so you can understand the math. But it would be better to use a loop to convert a string key to a number. What I'm going to do with this loop is do char at 2, char at 1, char at 0. If you look closely, value is the large number we're calculating. P26 is the power of 26. 26 to the 0 is 1, so we're going to do 26 to the 0 power here. Now notice how this loop goes backwards. Int I equals key dot length minus 1, I greater than or equal to 0, I. What we're going to do is grab char at 2, then char at 1, char at 0. This loop is going backwards through my key. If you follow the loop carefully, look at this line. P26 equals P26 times 26. What's that doing? Well, if this starts at 26 to the 0 power and you multiply it by 26, you get 26 to the first power. And you're multiplying next time by 26 to the first power. If this is 26 to the first power and you multiply it by 26, what do you get? You get 26 squared. And the next time through the loop, this is going to multiply by 26 squared. What I did is I converted the old code to a loop, and I'm using math to figure out the positions of the characters and the powers of 26. Value could get large. If I send a large key to this, I'm going to multiply by 26 cubed, 26 to the 4th, 26 to the 5th. Value could get very large. That's the reason why I declared value to be a long. And then after I do my math, value modulus 13, I'll convert it back to an int. This int has to be less than 13, so it will not overflow. You might want to pause the video at this point. I know this code is a little bit tricky, but it's not that bad. If you sit down and write out one of these keys, ace, bat, or con, and trace this code for one of these keys, you can see it produces the exact same result, except it uses a loop rather than all those hard-coded values that we used in the previous version. There are many different ways to convert a string to a number. The loop shown here is certainly better than the simple technique shown before, but there are even stronger algorithms that exist. If a key contains more letters than A to Z, you're going to have to use a power higher than 26. So you really do have to worry about overflowing the integer. You might even have to worry about overflowing a long. There's many mathematical techniques that do this same thing, convert letters to a number, without using very, very large numbers. But for now, let's try and understand this code and certainly understand the math. Any string can be converted to a number, no matter what technique you use. It's not that hard. Then you just do a modulus on the array size, and you can store string keys in a hash table. Next up, hash collisions. A hash collision is when two or more keys hash to the same location. You can't park three cars in one parking spot, and you can't store three elements into one array slot. Here's the problem we're dealing with. Hash function 1, using input key 1, sent the output index of 4, and we wanted to store input key 1 in slot 4 of the array. Then I called hash function 1 again and passed it a different input key 2, but it sent an output index of the same slot, position 4. Well, input key 2 wants to go in the same slot as input key 1. Oh, let's make it even worse. Hash function 1 is called with an input key 3, a different key. It output index of the same 4. All three of these keys, key 1, key 2, and key 3, want to go into the same position, slot 4 of the hash array. Even the best hash functions can calculate the same value for different input keys. In that case, the first element gets the spot, and the others must find an alternative place in the hash table. In the example above, input key 1 got there first, so input key 2 and input key 3 must find a different place in the hash table. Hash collisions. First and foremost, to prevent collisions, allocate extra free space in the table. Collisions increase when the table goes beyond 50% used and can dramatically slow the table as it reaches past 75% used. So if you always have plenty of free space, you can avoid collisions. The second thing you can do is use prime numbers in your calculations. When you're calculating the remainder, make sure the second operand is a prime number, and it'll spread out the data, reducing the number of collisions, but not eliminating it. When you do have a collision, there's several techniques you can use. Let's look first at linear probe or linear probing. Let's say x equals hash 1 with the argument of 240 returns 6. Index x is used by 123. I want to insert the new value, 240, into this position right here of the array. Well, if that's occupied by something else, try x plus 1 or position 7. And x plus 1, we see there's a 383 at that position. Let's try x plus 2 or 8. And if that's free, let's insert 240 into slot 8. When a collision occurs, keep trying the next slot until an empty slot is found. Linear probing just says increase by 1 until you find an open slot. When retrieving 240, it's important to follow this same x plus 1, x plus 2, x plus 3 pattern. We're going to say x equals hash 1 with the argument of 240. Once again, it returns 6, and it says you should find 240 at position 6 of the array. Well, index 6 is occupied by 123. When retrieving data, not inserting, but when retrieving data, you go to slot 6, it's occupied. You go to slot 7, x plus 1, and it's got a 383. That's not what you're looking for. So you try x plus 2 or position 8, and you find 240 in slot 8. What happens if you were to find an empty slot before you found the data you're looking for? Well, that tells you the data is not in the table. The probing happens on both sides. It happens when you insert the data, and it happens when you go to retrieve it. The spot is occupied, so you got to look through the table for what you're looking for. Linear probe tends to cluster or bunch things up, so an alternative is called a quadratic probe. Let's say x equals hash 1 of 599 returns a 1. Insert 599 into position 1 of the array, and index 1 here is occupied. It's used by 456. Let's try x plus 1 squared or position 2 of the array, and you can see it's occupied by 313. Let's try x plus 2 squared or position 5 of the array, and it is free. Insert 599 in slot 5. If slot 5 was occupied, we would have tried x plus 3 squared or slot 10. We need free space. None of these probes work unless you have plenty of free space in the table. As long as your probe amounts are not too long, You don't have to probe through the entire array. Then probing is a reasonable solution to collisions. It just means occasionally something's going to have to search for a spot in the table or do a probe to locate some data. The pattern for quadratic probing is step number squared. On the first try, you go to x plus 1 squared. On the second try, you go to x plus 2 squared. And on the third try, you go to x plus 3 squared. When searching for 599, do the same thing. X equals hash 1 of 599 returns a 1. 599 should have been stored in slot 1 of the array. But index 1 is occupied by 456, so we'll try x plus 1 squared, or position 2, which is used by 313. So try x plus 2 squared, or 5, and we find the 599 in slot 5. Follow the same sequence that you did in order to insert the data, and you will eventually find it. If you follow the sequence and you find an empty slot, that means the search fails and what you're looking for is not in the table. A third option is called double hashing. That's where we run a second hash function to find a second hash amount, or the probe amount. Let's say x equals hash 1 of 263 returns a 3. When we go to position 3 of the array, we can't insert 263 there because it's used by 549. So we call a second hash function, we'll call it double hash, using the same key, 263, and that returns a 4. That means we want to add 4 to probe the array. If x is occupied, try x plus 4, or position 7. At position 7, we find a 692, it's occupied. So now let's try x plus 8, or position 11. We found position 11, it's free, so we're going to insert the 263 in slot 11 of the array. Notice these gaps between the data. Gaps are good. We don't like it when the data bunches up. We like it when the data spreads out. And double hashing does a slightly better job of preventing these clusters than linear probing or quadratic probing. All it is running a second function to determine the amount you increase by. Linear probing says go x plus 1, x plus 2, x plus 3. Quadratic probing says go x plus 1, x plus 4, x plus 9. And double hashing says go to x, x plus 4, x plus 8, x plus 12. Now, of course, when you're retrieving the same data, you've got to follow the same pattern. If x is occupied, try x plus 1 times the second hash function result. If that's occupied, try x plus 2 times the second hash function result. And if that's occupied, try x plus 3 times the second hash function. When we're searching, x equals hash 1 of 263 returns a 3 like it always should. And it's occupied 549, it's not 263. So we'll calculate a second one. A second hash function, it returns a 4. Again, double hash, pass it the same key, returns the same 4. And it says add 4 to the probe amount, or probe the array by plus 4. Try x plus 4, or position 7. So that probe says I got a 692 there, not a 263. So let's try x plus 8. When I try x plus 8, or position 11, I find my 263 in slot 11 of the array. Once again, if I'm probing and I encounter an empty slot, then my search failed. Collisions add a little bit of complexity, but it really is just a matter of if position is occupied, go on a search. Search through a consistent set of numbers in order to find a new spot for your data. Another technique is very different. It does not involve probing. It's called separate chaining. If x equals hash 1 of 23 returns a 10, index 10 contains a linked list. Elements 36 and 10 had previously been inserted in position 10, so we simply add 23 as the first item in the linked list. Now, this separate chaining is good if the lists are not that long. As long as I have short linked lists at each slot, this is a good technique for resolving collisions. What we're really doing here is we're creating a linked list of all the items that hash to index X. When it comes time to searching for that same item, X equals hash 1 of 23, it returns a 10. I go to slot 10, I traverse the linked list, and I find it right away. If what you're looking for is not in the list, then it's not in the table. This is also a good solution if you have duplicate keys. Normally in a hash function, you would love to have all your keys to be unique. But if you do have a situation where you have to hash data in a hash table and you can have duplicate keys, separate chaining is a great solution because all the duplicate keys will be in the same linked list. Let's look at some code that deals with collisions. We're going to say slot equals hash 1 of 240. We're going to call the hash 1 function and find out where 240 should go. Calling method hash 1 and asking for the index slot to store 240. Using a hard-coded 240 so we can see the math, but keep in mind this would be a variable that contained 240. Here's the math. When you divide the key 240 by 13, right here, do the calculation, you'll get a remainder of 6. That remainder of 6 will be returned for the slot number, and it says 240, if it can, would like to go in slot 6. But there's a problem with slot 6. It's occupied. We're going to get a collision. This is on the insert. This is the loop that we're going to run when we're trying to insert new data into the hash table. While hash array of slot is greater than 0. Well, 123 is definitely greater than 0, so slot 6 is occupied. We must do a linear probe to slot plus 1, etc. for an open array slot. What we're going to do is, while a slot is occupied, add 1 to slot. This is the linear probe. Bump the slot plus 1 and look for an open index in the hash table. Looping back up, while hash array of slot is greater than 0, well, 383 greater than 0 is still a true statement. As a true statement, slot 7 is occupied. We must linear probe to slot plus 1 for an open array slot. Slot plus plus is the linear probe. Bump to plot 1 and look for an open index in the hash table. The hash array of slot greater than 0. 8 is unoccupied. 8 is free. It contains the value -1 to indicate that it's free. We found an open array slot. Let's exit this loop and insert 240. Note, free slots contain -1. I'm not showing a -1 in every one of these slots just because it's too cluttered when it does. But let's just use -1 as our indication that a slot is open. And this loop will exit when it finds that -1. When it finds that -1, it'll exit the loop, and wherever slot happens to be, which is a free slot, it'll insert the 240. Linear probe located the free slot 8 and inserted 240 at index 8, and the insert is done. Now, of course, when you use linear probing when inserting new data, you're going to have to do the same probing when searching for the data. Let's set my key equal to 240, the same key that we inserted up here. When we wish to search or retrieve 240, a slight change to the linear probe loop is needed. We need to look for the key or a -1, which means the item was not found. We'll say slot equals hash 1 and pass it my key and send that as the argument to the key parameter. Calling method hash 1 and asking it for the index or slot to start the find for key 240 in the hash table. Let's do the math. 13 divided by 240 is 18 with a remainder of 6. When you divide key 240 by 13, the remainder of 6 is returned and the slot number starts at 6, which is really where we start the probe from. While hash array of slot does not match my key. Well, the array contains a 123 in position 6 of the array. And we're looking for 240. They don't match. That's a true statement. We must linear probe to slot plus 1, etc. and look for 240 or an open array slot of -1. Here's our linear probe. We bump to slot plus 1. We're going to look for my key if it's found, or an open index in the hash table, which indicates it's not found. Hash array of slot does not equal my key. Slot 7, 383, does not match what we're looking for, 240. That is a true statement. Slot 7 is not 240. We must linear probe to slot plus 1, etc., and look for 240 or an open array slot of -1. Here's our linear probe. We'll bump to slot plus 1 and look for my key, which means we found it. Or if we reach an open index in the hash table, it means our data is not found. Hash array of slot not equal to my key. Well, in slot 8, we have a 240. Not equal to 240 is a false statement. Slot 8 is 240. The linear probe is done. We are going to exit this loop because this condition went to false. When we exit that loop, we found our data. At the end of the loop, if hash array of slot equals my key, then we'll return slot number and say we found the data in slot 8. But at the end of this loop, if hash array of slot equals -1, we'll return a -1 to say we couldn't find the data. Probing adds a little extra work to storing and retrieving data from the hash table. Hash table performance. Hash tables are the fastest data structures. They calculate, not search for the data. They are big O, order of 1. To understand why hash tables are fast, big O order 1, you need to understand big O is a relative measure of a data structure's performance as n increases. As of the moment I am speaking right now, the current world records in the sprints are 100 meters is 9.58 seconds, 200 meters is 19.91 seconds, and 400 meters is 43.03 seconds. As expected, the longer the distance, the longer it takes to run. You double the distance, you would expect it to take at least twice as long to run that amount. Well, big O measures how much longer it'll take as the data size n increases. Most data structures slow down as n increases. If n doubles, you would expect it to take twice as long. Let's say n increases 10 times. Number 1, insert into an ordered array takes 10 times longer, or big O order of n. Big O order of n says as I double my data, it doubles the time it takes to find or search or do whatever to that data. Well, let's say we do an insert into a balanced binary tree. Balanced binary trees take slightly longer. It's called big O order of log n. If I go from a 10 level tree to a 12 level tree, I expect my data to take slightly longer, but not much longer to insert into a balanced binary tree. But an insert into a hash table takes no extra time. That's why it's order of 1. If I insert data into a hash table with 100 items, how much longer will it take to insert data into a hash table with 1,000 items? How much longer will it take to insert in a hash table with 100,000 items? The answer, it doesn't take longer. A hash table is like if the sprint times were all 9.58. So it took 9.58 seconds to run 100 meters. And if it took 9.58 seconds to run 200 meters. And it took 9.58 seconds to run 400 meters. Big O order of 1 says I don't care how big the hash table gets. It takes the same amount of time to insert and retrieve from it. Now, one caveat, there has to be plenty of free space in your hash table. If your hash table is 90% full, it could slow down to order of n. To understand why hash tables are order of 1, the array to the right has 103 slots. Now, I can't show 103 slots, so I put some dots in there to show you that it goes from 0 to 102. I have 103 slots in my array. To insert the key 456, we would then have to do a modulus 103, because that's the size of my array, and it would equal 44. It calculates where to store or find the 456. If you do the math, 103 into 456 goes into it 4 times with a remainder of 44. We need to insert 456 into position 44 of the array. It does not scan many slots looking for the index to place 456. It does not navigate down a tree to locate the place to store 456. A hash table calculates the index 44 and instantly jumps or places 456 into the array at that position. To understand why hash tables are order 1, the array to the right now has 1,009 slots. From 0 to 1008 is 1,009 slots. If we wanted to insert the key 9347 into this array, we'd have to do a modulus of 1,009 and it would equal 266. This calculates where to store or find 9347. If you do the math, 1,009 goes into this 9 times with a remainder of 266. 266 is where we want to store the key 9347. Hash tables are like the transporter in Star Trek. We're going to calculate where 9347 should go and beam it directly to slot 266. We're not going to search 250 slots to find a position for it. We're going to go straight to 266. If the Star Trek transporter takes the same 30 seconds to beam someone 1 mile, 10 mile, or 100 miles away, it's an order of 1 beam. That's the beauty of the transporter beam. It takes the same amount of time to send you a block as it takes to send you a mile. Hash tables beam directly to the spot you want to go. The array to the right now has 10,007 slots. These may seem like strange numbers, but these are all prime numbers. 10,007 is a prime number just past 10,000. To insert the key 56234, do a modulus on 10,007, and it calculates 6199 is where I should store and find 56234. Well, if you do the math, it goes in there 5 times. 5 times that is this, and my remainder is 6,199. That's where I want to store the key 56234. What you need to understand is all of these calculations take the same amount of time. 56234 modulus 10,007 equals 6199. 9347 modulus 1009 equals 266. 456 modulus 103 equals 44. These are all 32 or 64-bit calculations. It takes the same amount of time. Frankly, you could make the array size the first prime number past of 1 million, and it would still take the same amount of time. Now, if it takes the same amount of time to insert into a table of 100 or into a hash table of 1,000,000 slots, that is an order of 1 algorithm. With that one caveat, remember, very full hash tables can cause slowing because of long probes. If I have a hash table with 1,000,000 items and I have to search through 100,000 slots to find some data, that's going to slow me down. But as long as I don't have large probe amounts to find open records or to locate my data, hash tables work at order of 1. If hash tables are so fast, why use anything else? There's 2 disadvantages to hash tables. Return to the example where we store the players in a large online video game into a hash table using their screen names. It requires we convert the screen name to a number and using the modulus to calculate the array slot in which we store the player records. During gameplay, we have a fast way to look up and update player information. Disadvantage 1. Extra memory is required. See all the empty slots in this hash table? We have plenty of empty room in here. This is a requirement. Unused memory needed to maintain order of 1 speed. Studies have shown when the table exceeds 50% used, it starts to slow down. Insert when the table is 90% full could slow to order of n speed due to long probes. If I have to search through 90% of the array to find an open slot, oh boy, it's not going to run at order 1 speed. Now, what if we need to store 1,000,000 records? Very large online games could have 1,000,000 players going at one time. We need to allocate space for at least 2,000,000, and that's a lot of extra space. But it's a requirement. There's no such thing as a perfect hash function. All hash functions have collisions. All collisions may lead to probes, and extra long probes could slow down our performance. So you've got to have a lot of extra unused space. Number 2, disadvantage. No sorted access to the data. What if the game wanted to show players who else is logged on so they can find their friends or their rivals? If you've played an online game, you want to know if your buddy is online at the same time. The best a hash table could do in showing you the list of the players logged on is to give you an unsorted list. It could say, I can tell you that con, elk, ace, bat, etc. are logged on. And if you notice, it's just going down in order of this array. It's difficult, downright hard, to find a specific screen name in an unsorted list if there are thousands of players logged on. If you're looking for your friend and you can't see an alphabetical list of screen names, it's going to be hard to find out who's logged on to the game. In this situation, you may want to see who's logged on in an ordered list. If sorted access to the data is a requirement, perhaps a tree data structure may be better than a hash table. Choosing the proper data structure before you start coding is the core of a computer science education. If it is a requirement to show the other players in an online game a list of who's logged on, you'd kind of like to see that list in order. Well, trees offer up in-order traversals. An in-order traversal of tree will show you who's logged on to the game in alphabetical order. Ace, bat, cat, con, and so on. The only way to get ordered access to the data is to use something other than a hash table. And that's really what we're trying to learn here. When do I use a hash table? When do I use a binary tree? When do I use a linked list? The key to successful software development is in the design phase, when you are deciding how to solve the problem, choosing the right data structure. When you choose the proper data structure, the problem is easy to solve. The code is simple. When you choose the wrong data structure, the problem is difficult to solve, and your code becomes very, very hard to deal with. A hash table is the go-to structure when speed is the highest priority. But a lack of sorted access means tree structures are still an important option. Building hybrid structures are also a possibility, but keep in mind they operate at the speed of the slower structure and do require extra memory. You can build a tree hash table hybrid data structure, but it's going to run at the tree speed. Thank you for listening to this lecture on hash tables. Good day.